Okay, so this video is for section 1.4 on combining functions. So creating new functions from other functions, or eventually, like in calculus, it's helpful to, when you have a function that has multiple parts or is a little more complex, it can be helpful to think about that function as being a sum or difference of other functions, or a composite function, like one function inside of another function. So we're going to look at combining functions or creating new functions from performing some basic operations, so from adding, subtracting, multiplying, and dividing functions, and then also composing functions, so evaluating a function at another function, and then determining the domain of all of those resulting functions. So we'll first look at adding, subtracting, multiplying, and dividing functions. So if you're given two functions and you want to perform one of those operations, you just add, subtract, multiply, or divide. And then sometimes you can simplify the equation of that new function, but you are creating one new function from other functions. And all the examples here are just dealing with two functions, but you could also think of like adding three functions together or more. Okay, so let's look at a few examples. So given the function f of x equals to the square root of x minus 1, and g of x equals to 2 times the square root of 3 minus x, I'm not sure why that symbol is underneath there. Let's create a new function from adding those two functions together. And this is just using function notation. So the name of this new function would be f plus g, but we could name it something else. Like we could call it h of x or t of x or something, but f plus g is the name of the new function that we get from adding those two functions together. So f of x plus g of x, I take the function f of x and then add the function g of x. There's nothing that we can do to simplify. It's not in the directions, but for each of these, let's state the domain of the new function that's created. My suggestion is going to always be to look for domain restrictions when you first create the new function. So in the first step, before you do any sort of simplifying, or at least any sort of major simplification, and we'll run into those in these examples, check for your domain restrictions then. So notice that we can't simplify the equation for this function any further. The square root, what's underneath the square root is not the same thing, so we can't combine like terms. So we'll just leave this equation as is. Now notice that because we do have the two square roots, we have two domain restrictions that we need to pay attention to in order to state the domain of this function. So we know, I'll do my work off to the side here. Maybe I'll switch colors just so keep the work separate. So we see that for that first piece, so from the function f of x, x minus 1 would have to be greater than or equal to 0. Okay, and that's just a linear inequality. If we solved, we would get x has to be greater than or equal to 1, which in interval notation would be written as 1 to infinity, where 1 is included. And then if we look at that second square root, which comes from the function g, we know that 3 minus x must also be greater than or equal to 0. And if I'm just going to add x to each side here, and if I flip that around, I get x is less than or equal to 3. So in interval notation, that would be written as negative infinity to 3. Now we need to take into account both of those domain restrictions to state the new domain for this function. Not the new domain, the domain for this function, which comes from thinking about the domain of each piece. We have to satisfy both of those domain restrictions. So the domain of this function is actually going to be the intersection of each of those intervals, each of the domains of f and g. So I can write that the domain is the intersection of 1 to infinity and negative infinity to 3. That can be simplified to be written as the interval from 1 to 3. And if you were to think about graphing each of those intervals on a number line, and then looking at where the intervals overlap, so if I put 1, 2, 3, 4, about 0. So like if I graphed 1 to infinity, that would be closed circle, and then I would graph to the right on the number line, or shade in to the right on the number line. And let's see, if I use orange for the interval from negative infinity to 3, 3 would be included, and then we would shade to the left. So you can see that that overlap happens on the interval from 0 to positive 3, right? So that is the domain of the function f plus g. Okay, let's use a new color for our next problem. Let's use the lighter blue. Okay, so the equation for f minus g, again, f minus g is the name of the function that we're creating from subtracting the function g from the function f. Pretty straightforward. I will take the function f of x, the equation for it, or expression for it. So square root of x minus 1, and then subtract g of x, so 2 times the square root of 3 minus x. Again, just like the previous example for f plus g, we can't simplify this any further. For domain, right, we would end up with the same domain restriction. So we can also say that the domain of f minus g would be from 1 to 3. Okay, now we're going to create a function for multiplying those two functions. So we take function f, so the square root of x minus 1, and then we are multiplying it by g, which is 2 times the square root of 3 minus x. This equation can be simplified. So remember, when we're multiplying, so square root of a times the square root of b is equal to the square root of a times b. And that just goes back from exponent rules. This is equal, I can bring the 2 out front by the commutative property of multiplication, and then I can write this as the square root of x minus 1 times 3 minus x. And if I wanted to, I could multiply out x minus 1 times 3 minus x, although there's not really a reason to. Okay, so let's see. For domain restrictions. You can actually look at either line here that we have. So you could find the domain by looking at the intersection of those two domain restrictions, just like we did in the previous two examples. But you can also determine the domain here just by looking at this second line. So when we did multiply to simplify the expression that represents f times g. So you could take x minus 1 times 3 minus x, and we know that that has to be greater than or equal to 0. And then if we did the analysis line, because this is a quadratic, so 1 and 3 would be the values that you would put on your analysis line. This is a parabola, right? X minus 1 times 3 minus x. Oh, it would actually be a parabola that would open down, huh? Because if we multiplied that out, we would have negative x squared. So it actually is a parabola that opens down, meaning that the graph would go from negative to positive to negative. You can also think about doing actual test values. So like 0, 2, and 4, you could plug in, we get a negative value when we plug in 0. If we plug in 2, we get a positive value. If we plug in 4, we get a negative value. So the values that would make this a true statement would be between 1 and 3. So just like in the previous two examples, we see that the domain ends up being from 1 to 3, where 1 and 3 are included. Okay, let's create a new function from dividing the function f by the function g. So that'll be the square root of x minus 1 over 2 times the square root of 3 minus x. The only simplifying that I could justify doing here would be rationalizing the denominator by multiplying by a version of 1, and that version of 1 would be the square root of 3 minus x over itself. And when we do that, we would get the square root of x minus 1 times 3 minus x in the numerator over 2 times 3 minus x. And if you wanted to distribute the 2 in, you could, but you don't necessarily have to. Looking at that first representation of f divided by g, that's where I'm going to, that's what I'm going to use to help me determine what the domain of this new function is. I know that x minus 1 would have to be greater than or equal to 0, so x has to be greater than or equal to 1. Because the square root of 3 minus x is in the denominator, 3 minus x has to be strictly greater than 0. It can't be equal to 0 because it is in the denominator. So adding x to each side of the inequality there, I'm going to flip that around just so that when I read it, I can say x is less than 3. Oh, I forgot to write in interval notation. So just like before, x greater than or equal to 1 would be 1 to infinity, where 1 is included. And then x strictly less than 3 would be written in interval notation as negative infinity to 3, but 3 is not included. So our domain is the intersection of those two intervals. You don't have to think about it necessarily as finding the intersection of those intervals. Really, like, you could just kind of reason it out and think, okay, well, I have to take into account this domain restriction and this domain restriction, so what would make sense? And where these two intervals would overlap would be from 1 to 3, but 3 is not going to be included in the interval. So a little bit different than the domain of the other 3 functions that we created. So my suggestion, the textbook does have like kind of a general statement written out, but my suggestion is when you are creating new functions, because this will work for also when we're composing functions, is just take domain restrictions before you simplify. So let's look at composing functions next. Okay, and so if you were given 2 functions and you were composing them, you were evaluating a function at the other function. Or I always like to, when I think of composite functions, I think of like the Russian nesting dolls, where like when you keep opening up the doll, there's another doll inside. Studying composite functions will come up, or composite functions will come up multiple times. So when we are verifying that 2 functions are inverses of each other, we will be using composing 2 functions. There will be trig identities where we'll be talking about composite functions. And then next year in calculus, you're going to want, when you're trying to take the derivative or sometimes to integrate certain functions, you're going to want to think of them as being composite functions. So a function inside another function. And we typically use, just because f and g are really common function names, you'll typically see, like if you're composing the functions f and g, f composed with g, this is notation here, that open circle, not a closed circle. If it were a closed circle, that would indicate multiplication, but it's that open circle. I know I've heard other teachers refer to it as Fogg and Goff, but f composed with g is one notation, and then I kind of like what's used for the definition here, because you can really see that, okay, that's the function f being evaluated at the function g of x. Okay, and there's a little definition of the domain there, but again, I think it's helpful to just look at what the domain is from when you first compose and before you do any major simplifying. And then Goff, g composed with f, where g is on the outside, f would be on the inside. Okay, so let's, given f of x is equal to x squared minus 1 and g of x is equal to 2 minus x, let's find f, the new function f composed with g, as well as the new function g composed with f, and then let's also state those new functions' domains. So f composed with g that's f as the outside function being evaluated at g. I'm going to use multiple colors here. Put g of x as kind of that reddish pink color. So when coming up with these equations, okay, I'm going to take the outside function, which is f, and I'm going to use parentheses around where I would want to place the x, and then I'm going to be replacing x with the equation for g of x. So I'm going to be replacing x with 2 minus x. This can be simplified. You can leave as is, but this could be simplified by multiplying out 2 minus x times 2 minus x, and then subtracting the 1. So that would be 2 minus 2x minus 2x would be minus 4x plus x squared, and then that minus 1, and then combining like terms, x squared minus 4x plus 1. Notice that f and g, f is a quadratic and g of x is a linear function. Those are both polynomial functions. And the nice thing about when we're composing a polynomial function with another polynomial function is you just end up creating another polynomial function. And you guys should know that the domain of any polynomial function is all real numbers. So from negative infinity to positive infinity. Okay, and then doing G composed with F. Made that circle too large. There we go. So G is the outside function. So G using parentheses for where X would go. And then F of X is the inside function, and I'll replace the X in the equation for G of X with X squared minus 1. And then that can simplify just by distributing the negative. It's like distributing -1, and that will be negative X squared plus 3. Again, we've composed a polynomial function with another polynomial function. The domain just is still all real numbers. Okie dokie, so let's look at another example. These ones will notice that we have two rational functions here, two functions that are written as fractions, so we know that we are going to have some domain restrictions here. The domain of each of those functions is not all real numbers, right? We have to exclude some real numbers from the domain, so we will have domain restrictions for the functions that we create from composing. So let's find each of F composed with G and G composed with F and state their domain. So F composed with G be F as the outside function, and then G as the inside function. Okay, and then to simplify here, it's nice to simplify, at least get rid of any complex fractions. So fractions in the numerator or denominator. To get rid of the complex fraction, so that 1 over x that's in the denominator, I'm going to multiply by a version of 1. And the version of 1 that I'm going to multiply by will be x over x, so that I can get the denominator of that complex fraction to cancel. So the numerator will be x, and then when I distribute the x to each term in the denominator, that ends up being 1 minus x. This is what I mean by you need to be careful about taking your domain restrictions and make sure you take them before you do any sort of major simplification. If we were to just focus on this final equation here, it would look like we would just need to exclude 1 from the domain of F composed with G. However, because of this 1 over x, x cannot be equal to 0. You can't have 0 in the denominator of any fraction, including complex fractions. And then if we took 1 over x minus 1 and said, okay, well, that can't be equal to 0 either, we'd have 1 over x equals to 1 when we add 1 to both sides, or it cannot be equal to 1. And then if we multiply by x on both sides, we would get that 1, or you could even solve that by inspection, just looking at the equation. X cannot be equal to 1. So the domain of F composed with G is negative infinity to 0, union 0 to 1, union 1 to infinity, so that we exclude 1 and 0 from the domain. I'm going to give myself an extra page just so that I don't have to squeeze my work for G composed with F on here. Let's use different. Okay, so G composed with F. That's G is the outside function. So since the entire denominator for G of X is X, is the variable, I'm going to replace the entire denominator with f of x, which is 1 over x minus 1. Oops. And that's 1 divided by 1 over x minus 1, which is just x minus 1. So looking at the simplified equation, x minus 1 has a domain of all real numbers. However, because of that complex fraction, when we compose the two functions, we can see that x cannot be equal to positive 1. So we need to exclude positive 1 from the domain. So to write that, that will be negative infinity to 1 union 1 to infinity. Okay, and I'm just trying to give you guys a few examples of where you could end up with some trickier domain restrictions from composing the functions. So f of x equals to the square root of 2 minus x, g of x equals to x squared plus 2. So let's first find f composed with g. Oops. So f is the outside function. And then g of x is the inside function. Now, combining like terms is not considered to be a major simplification. We can go ahead and distribute that negative and then combine like terms, and we would actually just end up with negative x squared underneath the radical. Notice that if you took from that first line 2 minus the quantity x squared plus 2 and said that has to be greater than or equal to 0, that when we simplify that left side there, we just end up with negative x squared must be greater than or equal to 0. This is a quadratic inequality. The only value that would make the left-hand side there equal to 0 would be 0. And that's negative x squared is a parabola that opens down. So we'll go from negative and then hit the x-axis and then go back to negative. So actually the only x value that would make negative x squared greater than or equal to 0 as true statement would be 0. So the domain of f composed with g is actually just 0, a single point. The graph would literally, if you typed the equation in for f composed with g, the graph would only be at the point 0, 0. Kind of crazy. Let's find g composed with f. So g is the outside function. And f is the inside function. Now remember, square root, or the radical, is the same thing as raising 2 minus x to the 1/2 power. And when you raise a power to a power, you multiply the exponents, and 1/2 times 2 would be 1. So this actually simplifies to be 2 minus x and then the plus 2. And when we combine like terms, we get negative x plus 4. So the simplified equation for g composed with f would be negative x plus 4, which is a line. However, if we go back to that first line when we compose g with f, we can see that 2 minus x has to be greater than or equal to 0. And if we add x to each side of the inequality there, oh, that's not 0, that should be x. And if I flip that around, I get that x must be less than or equal to 0. Or sorry, x must be less than or equal to positive 2. So the domain of g composed with f is actually from negative infinity to 2. I just think this is so cool. If you type this equation into your graphing calculator, and I want to encourage you to do that. So if you type that line into your graphing calculator, the graph is going to look like the graph of negative x plus 4, so the line that has a slope of negative 1 and a y-intercept of 4. However, the graph is only going to be defined from negative infinity up to 2, so it will literally stop. You're going to see that that's what happens when you're able to simplify an equation that ends up kind of getting rid of domain restrictions, is that the graph will look like the simplified version of the equation. However, it will have the domain restrictions from the original equation. Okay, and then just a little bit of practice evaluating a composite function. So if we want to evaluate f composed with g at 2, well, we think about f is going to be the outside function. G would be the inside function. And instead of putting x, I'm going to put insert 2. So that might have made it look a little more complicated than it needed to be, but let's think about this. Okay, well, the square root of 2 plus 2, that's the square root of 4, which is 2. And then when we square 2, we get 4, and 4 minus 4 would end up being equal to 0. Okay, g composed with f evaluated at negative 4. G is the outside function. F is the inside function. And we are plugging negative 4. That was maybe a bad choice of color. We are plugging negative 4 in for x. So that would be 16 minus 4 is 12, plus 2 would be 14, so the square root of 14. And the other way that you could have approached this is you could have found what the equations for f composed with g were and g composed with f, and also taken into account what the domain restrictions are, and then just plug the values into the simplified version of the equation. That's perfectly fine. By doing it this way, we will run into any, like if a value is not in the domain of the function. Okay, so f composed with g evaluated at negative 1. So f being the outside function, g is the inside function, and plugging negative 1 in for x. Okay, negative 1 plus 2 is 1. Square root of 1 is 1. 1 squared is 1. 1 minus 4 would be negative 3. And then g composed with f evaluated at negative 1. So g is the outside function. F is the inside function. Oops. And then if I plug -1 in for x, okay, that would be -1 squared is 1. So 1 minus 4 is -3, plus 2 would be -1. So this actually ends up being the square root of -1, which you guys know is an imaginary number. That simplifies to be I. So actually, -1 is not in the domain of G composed with F. Right? When we're talking domain, we're talking about where a function is defined in the real number system, not in domain of G composed with F. Okay, so the big takeaway here, what we've done in this section, we're creating new functions from performing operations or composing some given functions, and then just for finding the domain of the new function, make sure you take domain restrictions before you do any big simplifications.